This one's an interesting setup. This is a check the chop operation, and it shows what the settings are here. You'll notice that the source is external. And with that, the connection of the probe goes to the external connector on the oscilloscope, as I will show. And the oscilloscope is used to probe itself on a particular test point to produce a pattern on the screen, which will be evaluated. And what we're going to get is basically a sine wave, or what looks like a sine wave, coming out of both positions 1 and 2, right? And they want to look at the period or the cycle to see how big the cycle is based on these settings, right? So I have the probe plugged in here on external, and you can see that I am down at that test point, and I'm just connected to it right there. And this is what I got, and I have moved these into position as to be able to check exactly how long the period is to be measured, and I found it to be at 1.6 gradicules, and this is sufficient for this. It says 1.6 to 2.6 horizontal divisions. I figured 2.6 would be a lot, but you can see that it's 1 full division and then plus 3 dots at 0.2 per dot is 6. So that measured that. As far as I'm concerned, that's pretty much done. Disconnect the 10 times probe from the test point and the external input connector. Check 2 traces are visible for all for these particular settings that they show in section F. So we'll take a look at that next. The next step is the adjustment of the high frequency compensation, and it has specific settings that it wants put into the Tektronix oscilloscope, as well as a 1 megahertz 5 division square wave to be set up on the FieldTech, and that has already been set up, and I've hooked it into the oscilloscope here. It also specifically asks that the top of that square wave align itself to the center graticule. I've done that so as well. See the words HF comp just behind that cable down there, and if we go and we look at that cable, we see a forward blue potentiometer, and just to the left of it, a small open air capacitor. And those are the 2 adjustments that we're going to be working with in support of this step right now. Having aligned the square wave to the horizontal center graticule, they want me to adjust that capacitor now for 2% overshoot or 0.1 division as displayed on the CRT. So that's the first setting, is the adjustment of that capacitor, so I'll do that now. Interestingly, I find that based on the minimum, because when you turn these, they spin in circles, I'm really looking for minimum overshoot, because, I mean, the overshoot gets way above 2%, and I find that the minimum most closely aligns itself to the parameters that I'm looking for. So I'll tell you what, though, as you zoom in, you find there isn't really that much gains to be had. I'll fiddle with this, but I pretty much have a good corner on here, and I don't see much room for improvement. It then has you move to 5 millivolts per division, and readjust the frequency generator to produce 5 divisions again, and that zooms in even further and check for a plus or minus 4% correction in step J. And I've done that, and there's only 2 things here to work with, 1 capacitor and 1 variable resistor, and I believe I've brought them in as good as I'm going to bring them in. And what it then has you do in step K is repeat J through all of the following 5 millivolts to 0.5 volts. Adjust the generator output, obviously, for each one to get the 5 divisions again in doing so. So not doing any more adjustments, there's 10 again. Move to 20. And that right there is 20 millivolts. And that right there is 50. And I already have to say that's very respectable for 1 megahertz sine wave. But there's 50 millivolts right there. And there's 0.1. And just to bring in another one, you can see how clean that is. There's 1 megahertz, looking good. That's 0.1, and this is 0.2, and then I'll bring it in again. There's 0.2 right there, and there's 0.5. So it looks good to me. You can see a little bit of ring there in the beginnings. That's normal, but I don't think we're done with sine waves yet, honestly. But yeah, that's where we are right now, and this is not done by any means. This is just like halfway through this. So now everything's going to move over to channel 2, and we're basically going to do the same thing again. And channel 2 was configured at 10 millivolts initially, just like channel 1 was. So I'm going to do this right quick and just finish up channel 2 doing the same thing, and then I'll come back to here. Looks like channel 2 is sitting way down here under the CRT. I'm going to zoom out so we could get a look of where that's located. That's under there. It's on an angle, so it has to be hit from here. So that's where the channel 2 is set up. Not very convenient. The channel 2 capacitor was unpleasant to work with, had minimal but noticeable effect. I've locked it down in minimal position, and that's as good as it gets. There is no resistor for channel 2, only a capacitor. And I'm going to go through all of the other ones. I'm not going to do it on video, all of the different settings as prescribed in section J, I believe, to get past this step. Yeah, adjusting the capacitor in channel 2 is very difficult. There is no resistor. I adjusted it. It was very slight, minimal effect, but however minimal, it was a dip. And now I'm going to do I through J as written here to check through all of them. I'm not going to do it on video as I did just before. I've gone through and viewed all of the different voltages up to the last 1.5, and everything looks good for channel 2, so I'm going to say that this step is concluded. This next step didn't do a whole lot for me. I guess I also run into problems when I have to do things at 2 millivolts. I set up exactly as they stated, and I had to use my attenuator to the best of my ability, and I'm really driving this thing to nothing in order to do that. And the thing is that I can't use my resistor because I'll introduce too much interference into the square wave and have all sorts of distortion. So this is the best I got. So this introduces problems of its own, but it's less of a problem, right? And I'm looking to get this display, there's 5 divisions, right? And it says set the top of the display to center horizontal graticule, like just before, and then adjust the channel 2 millivolt peak comp 76 for 2% over the shoot of the display signal. 2% overshooted display signal, right? But if you look at the overshoot of this signal right here, right? I'm not going to go and do it because it's difficult to do while it's in the machine, but I could adjust this capacitor and it will go up and down like up here. This is way above 2%. And I don't see how this adjustment is going to bring this in or out or around 2% of what I'm trying to get into. So it seems like a meaningless or arbitrary adjustment for me. And part of the reason may be because this looks like crap. And the reason why it looks like crap is because I got the Fieldtech, and yeah, the Fieldtech produces crap. It doesn't look any better on the Hantek, I assure you. This is a limitation that I have. I'll think of something if I have a better way to produce something at 2 mil, you know, with 5 divisions. 10 millivolt square wave, but yeah, maybe if I could introduce less noise and have less ring, I'll be able to dial that in better. Yeah, that same nasty ring is sitting there on the Hantek too. So there's no way for me to take care of this unless I'm able to alleviate this problem from the signal itself. Yeah, I've decided I'm just going to move past this one. I don't have a function generator that could reliably produce this kind of signal the way I need it to. In such a way to conduct this particular step. Step 14, check trigger view gain. So 0.1 volts, 0.2 milliseconds, connecting up a basically another square wave into channel 1, and I'm centering it onto the oscilloscope, and then I'm hitting the trigger view button and then vertically centering it. And what they want me to look at is when I hit the trigger view button, based on the 5 graticules that the signal is that it's an amplitude of 4 to 6 divisions, 4 to 6 graticules, while the trigger view button is pressed. So let's take a look at that now. So this is the square wave. I just have it really fast, so it just looks like 2 lines. And it is exactly 5 graticules. I've just centered it. I've moved the position up and down so it sits exactly in the middle. And the next thing that was asked was to hit the trigger level button over here and then center that with this A level over here. I've already centered it. So when I hit the trigger level button, you'll see that it collapses somewhat. But even though it collapses, I could still count the four gradicules, or the four divisions, plus 1, 2, and 2 halves, 1, 2, 3, 4.3. So it's definitely between 4 to 6 divisions as far as the test goes. And now they want this replicated in channel 2. Channel 2 looks pretty much the same as channel 1. When I hit the trigger view, it's still between 4 and 6 divisions. So channel 2 looks fine as well. Now they want the cable removed from the channel and put into the external source. The external input switch selected, and repeat that test again with CND. So I'll do that now. Cable's on external input. A source is set to external. And we have just a line, obviously, since we have no input. And then I'll hit the trigger. And we can see that it is still about 4.5 divisions. So that passed that test as well. Now it asks that the A external coupling be set to DC. I have done so. And repeat the test yet again. So here we go. And we're still looking at about just about 4.5. So still between 4 and 6. So this is good. Now it says A external coupling to DC divided by 10, which I have set. The generator now be set up to a 5-volt signal, which I've done and verified on the Hantek. I plugged it back in with the DC divided by 10. I run the test again, and we still see that it's about 4.5 divisions, so it is good. And that concludes step 14. The next step is 15 and checks the position range. I had to read this a couple times to figure out what was going on, and found a typographical error, as noted here in B, should say channel 2. And once I got that straightened out, basically 50 millivolts AC set to internal. What they're looking for is a 0.5 volt signal on the input, and change the calibration knob as such that there is 4 divisions and 0.4 for the sine wave. And I had to read this a couple times because it seems rather strange until, like all these steps, you got to read it 3 or 4 times to figure it out. So it's 4.4 divisions is a display. And what they're looking for is, having this centered, I should be able to take the position knob and clear the top and the bottom after, mind you, after I go and change the value to 10 millivolts, right? So I just wanted to display that first. So I'm going to go to 10 millivolts, and now we can see the waveform is much bigger. And the bottom of the waveform should be able to go past the halfway point, which it does. And the other side should be able to go past the halfway point, which it does, right? And that's the test. That's all there is to it. There's nothing else to be done. So now I do it for the other channel. And here's channel 1 all set up. I turn it all the way up. It clears the halfway point. I turn it down. It clears the halfway point. We're going to call that step done and move on to 16. There is a cautionary note that reminds you to let this warm up for 20 minutes before proceeding. I've actually stepped away and did 15 really quickly here. I'm going to have to wait a while before I do step 16. So this one is self-explanatory, but I don't know if I'm going to be able to pull it off. I'll explain. We're setting up a waveform here at a given seconds per division with a bandwidth limiter in. Okay, and it's 50 kilohertz as such that it's going to be 6 divisions. And that's how they want it set up. And what they're asking for is to increase the frequency, the output frequency, until the frequency response drops to 4.2 divisions. And at that point, check the frequency on the generator, right? Check the frequency on the generator to see if it's between 18 and 22 megahertz, right? That's all well and good. As a matter of fact, I've already got the first portion set up right here. So it's ready to go at 50 kilohertz. Problem is, it's a FieldTech. Gotta love to hate the FieldTech. And the problem is that the frequency response is terrible on these things. It's not linear. So aside from the response of this bandwidth limit, right, the 20 megahertz bandwidth limit, the FieldTech won't put out a constant amplitude as I increase the frequency. But what we're going to do anyway, just for sort of an academic purpose, is I'm going to go along and do this test. This is about as good as I could get it set up here. It's a 0.05 megahertz, and I'm just going to start increasing this. And I guess I should go to tenths, so we're not going to be here all day. And we're 2 megahertz, 3, 4, And now we could see that the waveform is starting to drop. And 14. And now it's dropping a lot quicker. 17. I'm going to zero this in. I'm going to come back to it when I get right to the point I want to be. As it turns out, I went just past it. It happens to be exactly 4.2 divisions at 18.7. In the book, it says 18 to 22 megahertz. So technically, this value is within specification. But as I pointed out earlier, the Field-Tech is not entirely linear. So I wouldn't use something like this to validate this test. What I will do is check the other channel just to see if it falls out around this very same value. The other side is showing 18.3 for 4.2 divisions. So I'm calling that equal characteristics roughly. So saying that's good. Moving on to the next step. So 17 is a bandwidth check, and they want the bandwidth limit off. Set up a 50 kilohertz signal that takes up 6 divisions. And they want an amplitude displayed of at least 4.2 divisions when the following changes are made on the generator. So at 2 millivolts, they want the generator cranked up to 90 megahertz. And at 5 millivolts all the way up to 5 volts, they want the generator cranked up to 100 megahertz. Well, the Field-Tech only goes up to 20 megahertz. So that is problematic. And initially I thought to myself, to the outrage of purists, I was going to hook up my Heathkit RF signal generator. And by the way, don't be fooled. This thing can do easily 110 megahertz with a very nice pure sine wave waveform, no problems whatsoever. The issue is that this thing is not linear, and the amplitude of the waves are different heights depending on the band chosen, between the bands, and as you go through the band spread, the wave amplitude changes. So, and that's known. I mean, that's just a characteristic of this device that's like 70 years old. So when you're doing something where you're measuring amplitude based on the changing of a frequency, yeah, well, it's not going to work. So unfortunately, I'm going to have to skip this section. Just to show you, though, how much better this RF signal generator is than the Field-Tech. And mind you, I'm going through this monstrosity here that I used to connect these cables, right? This oscilloscope is set up for 2 mil right here, right? So this is 8, right? This is 4 divisions. Look at that sine wave. The bandwidth limiter is off, right? So there's no filtering. This on, this off, right? Look how clean that sine wave is. That is next to nothing. That is almost no signal at all, right? There's just 8 millivolts, and it's beautiful. There is no way. There's no way the Field-Tech's able to do that. You saw all the things I added on and all the junk and all the garbage that was attached to it. And that was just, one concentric cable with a resistor on it. It wasn't this. This is just my little kludge. It is night and day. I would work with something like this all day long compared to the Field-Tech if I could. I got all excited with step 18 because I'm looking at step 18 and I'm like, hey, I'm going to be able to use the Heathkit after all to produce this 80 megahertz 5 division display. And I'm going through the step here and I'm trying to figure out what I'm doing wrong, and I come to the realization that I have to produce a 5 division step at 1 volt. And therein lies one of the limitations. This is an RF signal generator, and there's no way that this thing is going to produce a 5 volt output, not even on a good day. And the Field-Tech is not going to produce 80 megahertz. So it looks as though, to my best efforts, even with both generators, one doesn't produce enough voltage and one doesn't produce enough frequency. I'm out of luck on 18. We can see what's going on here. It's self-explanatory. I just don't have the equipment to do it. So I'm going to move on to 19 and hope for something better. This is one where I'm going to use the Heathkit RF generator. I don't have cables that don't exhibit the kind of properties for loss to do this. But I'm going to do the test anyway and show how it works. I can replicate it, but this isn't stuff I generally work with. I don't work with 50 megahertz signals. I generally work with audio frequencies. but I'm going to do the test. And instead of reading through this entire thing, I'm basically going to talk it out, right? Again, we're going to use the RF generator, and we're going to see how this works. And I've got my little kludge right here. And this is the best that I could do to put this together. And again, very lossy for 50 megahertz would be perfectly fine audio frequencies, right? This is terrible. What I've got is this. This is probably the main issue, is the fact that this is all the RF generator can spit out at 10 millivolts, right? Because a lot of the losses is in those probes. The other side of this channel, because they're tapped off the same side, is also the same. I've just noticed I just switched to channel 2. Channel 1, channel 2. Channel 2 is inverted, however. And because it's inverted, if I add them together, I should get a net loss here. So when I switch it to both, we could see that the loss is there, right? And that's what they're going for. So basically what they're saying is that if it was 6 divisions, and you set the subproperty, so if this was 6 divisions wide, then when you switched it to both, then this would be 0.6 divisions or less, right? So it would be basically, it would be 1, 2, 3. It would be bigger than this, right? But obviously this isn't to scale, and that would be the measurement of what this was doing, right? But I can't generate enough to be able to do that. So channel 1, channel 2, which is now off because I used position, and then the additive result of that, and that's what they're going for here. And then they have a test, if it doesn't work, to drop down to 50 kilohertz and see if that works, and jump back up to 50 megahertz. What they don't have is a solution to this if it doesn't work. Again, these are checks, they're not adjustments, and I wanted to point that out as well. So we got to see it happen. Nothing we can do about it if it didn't work, but I just wanted to include it here. 20 is an easy one. They have a specific setup, and what they want to do is get this set up and switch between ground and AC back and forth on both channels to see if there's any deviation of 0.1 divisions, which basically means any movement at all. I've got this all set up for the task, and I'll switch over to channel 1. I'll lower this for the camera. And basically what they want is just go like that. I see no such deviation. I switch over to channel 2, and that's AC. No deviation. So that test is done. That concludes this section, vertical, and the next section will be horizontal.